Hello, and welcome to Lesson 11 of this Introduction to Calculus with Wolfram U. The topic for this lesson is the chain rule. So let's begin with a brief overview of the lesson. So recall that if you have two functions f and g, then the composition of f and g will take the values of g and then plug them into f. So here's an example. You have f given by x square and g is just a sine function. So if you try and work out f of g of x, that's going to be sine of x and then the square of it. So it's sine of x the whole square or sine square x. Now, the rules we have discussed so far, the sum rule, the product, etc., cannot be used to find the derivatives of such compositions. But of course, D knows about them. And what's required over here is something called the chain rule. So the chain rule is what lets you find out the derivatives of compositions. And that's the topic for the lesson, the chain rule and examples for this very powerful rule. Let's begin with a statement of the rule. So if you have two functions f and g, and if f is differentiable at g of x, and g is differentiable at x, then the composition is also differentiable at x. And the main point now is that the derivative is given by g prime of x on the right and then f prime of g of x on the left. Here's an example in the abstract setting. So d of f of g of x is f prime of g of x times g prime of x. So if I said find the derivative of sine square x, you would first work out the derivative of sine x and then the derivative of x square and then plug in x with sine x. Okay, and you get back the answer 2 cosine x sine x. So here's a plot of the function and its derivative, and notice that the function sine square x is always non-negative, but its derivative can be either positive or negative depending upon which portion of the graph you're in. Okay, so as an example of an algebraic function with a composition in it, let's take the square root of x squared minus 1. Now, in this case, the inner function is going to be x squared minus 1, and the outer one is square root of x. So that's the composition in this case, g of h of x. So what you do is you work out the derivative of x squared minus 1, which is 2x, and then work out the derivative of the outer function, and there's the answer. D gives the same result, and here is a plot of the function and its derivative. Of course, because you're finding the derivative of square root of x squared minus 1, there's nothing on the left of 1 over here. Okay, so here's a trig function, cosine of x squared. Now, the inner function over here is x squared, the outer one is cosine x. So let's first set up the composition, and you get back cosine of x squared from g of h of x. So you work out the derivative of h, that's 2x, work out the derivative of g, and then that's the answer. And of course, D gives just the same result. And here is a plot of the function and its derivative. Let's go on now to talking about the power rule. Now, the power rule is a rule for finding the derivative of x raised to n, but you can make it even more powerful by just composing it with another function g. Okay, so if I gave you f of g of x with g being some function, then the chain rule says that the derivative is n times g of x raised to n minus 1 times g prime x. So for example, if I said find the derivative of x squared, x raised to 4 plus 1 raised to 100, you can find quite easily because all you do is you do 100 times that raised to 99 times the derivative of x raised to 4 plus 1, which is 4x cube. Of course, you don't have to use a positive integer. You could use a fraction, like in this example, or you could even use a negative number, and you get back the answer quite easily. So, in this very simple way, you can extend the power rule to find the derivatives of fairly complicated compositions. Okay, now if you have a product like over here, so f of x is a product of two things over here, 3x minus 2 the whole cube and 9x raised to 4 minus x plus 3 the whole raised to 5, you might think that the best way to do it is to expand f. Well, you could do that and then find a derivative, but that's going to be a long, messy answer. So a much better way is to use the product rule and the chain rule together. So you say first function times the derivative of the second one, and then the second function times the derivative of the first, and you get back the answer, which is the same as the earlier long answer. And in fact, D prefers to use the product rule, and of course, you should do that too. So given a fairly complex expression like this, you must try and use the best rules possible to get the most compact answer in the result, because then you can use it much more easily in future work. Okay, so let's go on now talking about multiple compositions. So the chain rule itself talks about the derivative of f of g of x as being g prime x times f prime at g of x. But of course, that would hardly be a chain which only has two links in it. So you can keep on this way and build up chains of longer and longer lengths. So let's say you got f of g of h of x like over here. Then derivative is going to be h prime x, and then g prime at h of x, and then f prime at g of h of x. So in every case, you fix the remaining functions or variables and work out derivative. So for example, if I gave you sine of cosine of x squared as your function, then the derivative would be 2x from the x squared, then negative sine of x squared from the cosine, and then cosine of cosine x squared from the outer sine over here. So the answer here is confirmed by D, and that tells you that given any long chain of compositions, you can apply just the same rule and get the result. So a similar example is the one I take up next, which is the cube root of cosine of x squared. So again, you start from the innermost function, x squared, then work out the next function derivative in the chain, and then the outermost derivative. So the answer over here is a fairly complicated function, but D confirms that it is correct, and you can plot the function and its derivative, and you get back this beautiful plot. So just to recall for you the procedure again, you work out derivative of x squared, the innermost one, work out derivative of cosine of x and replace x with x squared, and then finally work out the derivative of cube root of x and replace x with cosine of x squared. Okay, so as a final example, let's talk about simple harmonic motion. So simple harmonic motion is a motion that's given by this kind of trigonometric function. So here A is the amplitude. So think of a pendulum. The amplitude is how far it goes in one direction. Omega is the frequency, that is how fast it goes. And delta is the phase shift. So you could have two pendulums and they both have slightly different motions because they have different phase shifts. They start at a slightly different time and you get different phase shifts. Now, given such a simple harmonic motion, you can work out the velocity and the acceleration by working out the first and second derivatives. So here are the velocity and the acceleration, v and a. And notice that the acceleration is almost the same as the position, except that it has this negative omega square multiplying it as an extra factor. So what that says is that s double prime plus omega square s of t is equal to 0. That's something called a differential equation, which you will study much later in calculus. And the whole formula does the following: it prevents anything from evaluating. So if you do release hold, like I've done over here, then in fact you get back the result true, which says that the differential equation is satisfied by the simple harmonic motion function over here. Okay, so that brings me to the end of today's lesson. So to summarize, the chain rule lets you find the derivatives of many more functions, because you can work out the derivatives of products and powers, etc., much more easily with the help of this rule. Now, of course, you can build up a chain of any length, so you can use it more than once when a function is a composition of more than two functions. So those two statements summarize the lesson, but today's lesson is probably the most difficult one in our series so far. So do review it carefully, look at the exercises, and make sure you're ready for the next lesson, which is on implicit differentiation. So I'll stop over here. I hope you enjoyed the lesson. Thank you.